Okay, 7.11, Introduction to Solubility Equilibria. So, we know that solid salts can dissolve in water, right? We've literally done that, and it's common sense. You dissolve some solids, ionic stuff, it'll dissolve, hooray. Now, obviously, we've talked about how some won't because of the solubility rules, but I'm going to talk about that in a second. So, there is something called KSP, so subscript SP. And so KSP is the equilibrium constant for deciding if something is soluble or not. Okay, so it's still an equilibrium constant. It's still the same way products over reactants. It's just now talking about dissolving stuff. Okay? And so, again, we're doing the same kinds of calculations for K. Cool. So, reminder, back in Unit 4, you had to memorize this one solubility rule, where these things are soluble, these ions, and the rest we're assuming isn't. Unless otherwise stated in the problem, obviously. Cool. And so, quick little review with a little bit of new stuff, right? And so, as a reminder, the definition of solubility is how much something can dissolve in water, as we've already implied earlier. And so, here's an example of one kind of salt, sodium chloride. And so, if you have a water molecule with its various dipoles, we can see that the water can surround the sodium and it can surround the chlorine based off of the interaction there. Okay. And so ionic compounds, if they're dissolved in water, they become ions, just like here. And so they're surrounded by the water. Cool. So we have the polarity of the water, as I said earlier. We have the Coulomb attractions between ions here. And then we have the ion dipole IMF here and here. So those are review from various units, right? And so solubility rules, if you are given a reference, be able to use them. But if not, then you just go by the one rule to memorize. Now, as I said here, technically, all ionic compounds are soluble to a degree. Is it hella soluble or not so much? And so what do I mean by that? Will a lot of it dissolve, or will a tiny bit, but most of it stays, a solid not dissolved? And so technically, even if it's labeled as insoluble, there is a tiny amount that will dissolve. But since it's so tiny, it's so minuscule, we just straight up say it's insoluble because it's so minuscule that it's not going to make much of a difference. Now, when we write an equation for this process of dissolving, we can write it like this. So here's an example. And so I have a solid. I add it in water. And so I have it in whatever charge it is. There's 2 of them, and whatever charge it is, and there's 5 of them because of the original, compound. This, again, is just a random example. And so you can write a net ionic equation based off this. It's technically not a reaction. It is just an equation. It's dissolving. And so this is going to come real handy in this section. So make sure you're able to write a net ionic equation for dissolving. It's easy enough, but you should be able to do it. Again, as a reminder, a saturated solution, you're essentially reaching the solid amount that can dissolve at whatever temperature of the thing you're dissolving in, usually water in this case. And it's given usually in grams per liter or whatever other units you might be given. And then molar solubility is, molarity of ions in the saturated solution. So again, molarity is moles per liter. And so the, you can that's a new term for this section, the molar solubility, is you can calculate the molarity of these ions in a saturated solution. Okay, so KSP. So KSP, you're still writing a K constant, and it's still products over reactants. You can talk about the molar solubility of every single ion in the ionic compound in solution. So again, here is an example of this guy. And so the KSP is, I forgot to put the SP. Oh well, whatever. So notice I have my products here, and then I have nothing in reactants. Why not? Think about it real quick. It's a solid! You don't put solids in your equilibrium constant. You only put solutions if you're talking about concentrations, and then you only put pressures if you're talking about gases and pressure. So, there we go. Okay, so we talk about the maximum number of moles that can dissolve in 1 liter of solution, right? And one thing that students confuse the terms for is KSP and molar solubility. They're not exactly the same. You'll see why when we do practice problems. And the other thing about KSP, if I have a bigger KSP value, that means the solid, whatever solid it is, can dissolve more. It is more soluble. So if you have a low KSP, then that means it is it is less soluble, and if it's hecka low, then it's dang near insoluble. Again, technically a tiny bit is dissolving, but it's so minuscule, it's just is insoluble at that point. So here's how we define personally as what's soluble versus not. So if KSP is greater than 1, then it's going to be very soluble. If it is less than 1, not so soluble. So that's pretty much the point that we're going to be using. Okay, so before we talk a little bit about something earlier, identify the names of these guys. You should be able to name these. And then write the KSP expression real quick, okay? And then, as I said here, be careful. You'll see what I mean in a second. So go ahead and try this out. Pause the video. Ready? Okay. So, answers. CO2 is 2 nonmetals, not ionic. So you're not making a solution. We were only talking about ionic because it's cations and anions. So that's the trick one. Be careful. Now, we don't talk about manganese that much in this class. So if you didn't know that this transition metal had multiple versions, it's not a big deal. You should know iron has multiple versions, so you need the Roman numeral for that. But they're not expecting you to memorize which ones are, have multiple versions or not, but you should know the common ones because we use them as examples, like iron, for example. So make sure you can write these KSP values based off how many there are. So for example, zinc, there's 3 of them, so that's why it's a 3 here. Make sure you put your little charges and whatnot. So this should be pretty easy peasy for now. Okay, cool. So let's do an example problem with KSP. So what is the molar solubility of that with a KSP of that? So we're going to distinguish what KSP and molar solubility is by doing this problem. It makes more sense by just doing it. Okay, so as a quick little reminder, because there's a temperature given here. If you had a higher temperature for a solution, you can dissolve more stuff. If you can dissolve more stuff, you have a different KSP value. So just like any other K, the temperature does matter. We usually assume room temp unless otherwise stated. And again, just like in previous sections, if the temperature increases or decreases, you should be able to predict what happens to the K value based off, if it's an exo or endothermic thing. There's just so many things. Okay, so here is our salt getting dissolved in water. I forgot to put a little water here, but whatever, it's fine. And so I'm going to do a rice table. I'll show you why in a second. But for now, let's just set up the rice table. And so I'm going to set up what we know. Now, as a reminder, this part is not going to be part of K because it's a solid, so that's why I'm not filling this part up in the rice table. I never fill out the part of the rice table that has solids or liquids, so that's why it's crossed out. Cool. And so then we started with none of those in solution yet because it's a solid, right? And so then we're going to dissolve a certain amount, and there's one of each. And so then I got just X, right? So that's easy enough anyway. And so I have my KSP. I will literally put in my X values here, and then I use the KSP given in the problem. I solve for X. I math that right. Yay. And so I have my concentrations of both after has reached equilibrium. Now, if you notice, it's -5. That is real small. So that means this thing is not dissolving that much. So it is pretty insoluble. But it's, see, technically it's dissolving a little bit. It's just 10 to the -5 is so tiny. So tiny. Okay. So we can calculate how much is going to dissolve based off a certain amount of water we have. And so I just convert that real quick. And so I have the concentrations that was calculated in part A. And so I just converted it to moles per liter just so you can see where the units are coming from. And so I pretty much took the liters, the volume, and then I used the molarity to cross that out. And then I have grams per mole. And then I got grams. And so grams per mole, what's this? You should know this. This is a basic thing from beginning of the year. Molar mass of calcium carbonate. So moles cancel out, liters cancel out, I'm left with the grams. So I got the grams. Yay! Easy math. Easy peasy lemon squeezy. Should be able to do this. If this is an FRQ, lucky you. Okay, so here's your turn. Oh, it's an MCQ practice. That's nice. So even though it's an MCU practice, make sure to show your work anyway. So go ahead and calculate the KSP and then calculate the molar concentrations when it's dissolved. So try that out first. Ready for the answers? Bam, bam. I showed my work in my little orange box. Sis. Why didn't I do plural? I don't know. And so here's my work. I don't really have much to say because I showed my work. So, yep. Now, obviously, MCQ answers, depending on how they round, might not match the sig figs properly. So, for example, this is 1.965, and if it's 2 sig figs, it should round to 2.0. But based off these answers, I just pick 1.99. Oh, and also 10 to the negative. Like, none of them are close. So I just picked the closest answer. So College Board is not going to make it trippy where they're going to have 1.9 times 10 to the -8 and then 2.0 times 10 to the -8. They're not that mean. But, just be careful. Okay. And then I have my X values here. Now, you want to be careful about number 2 because you can see this is X here, right? Remember that I minus, so iodide ion, is 2X. So you want to make sure you do 2 times X in order to get the I concentration. So be mindful of that. Now, obviously, I didn't show the rice tables for these because you technically don't have to show the rice table. I just do a rice table because it's the same calculations as all the K's. But if you really, really, really understand it, you don't have to show a rice table for this. But I always like having a little rice table just because, easy peasy. Okay, so KSP, again, super easy stuff for the most part. You should be able to just calculate nice and easy. Cool. Okay, bye.